All right, friends and neighbors, welcome back to CCNA Chapter 11, Part 2. We are going to cover the rest of quality of service in this video. So as you already know, the key topics will be part of this, as will the do I know this already questions. Now, last time we covered part of the exam section, which was IP services, and in particular, the per hop behaviors for QoS, classification, and marking. We did that last time. So now we're going to continue that, and we'll finish off queuing, congestion control, and policing or policies, and shaping. Now, if we scroll about halfway down through this, we're going to hit the Part 2 key topics. So that'll be the queuing components, the low latency queuing. Now, the whole idea here is that you've got a queuing algorithm that performs the scheduling for the queue, and then strategies to use when you're queuing, and in that will be congestion management. And then some logical steps that we can take with shapers and policers that have a markedly different effect on traffic, and they have quite a big difference in their behavior as well. So just a quick reminder, when we were talking about our intro to QoS, right, we've got packets coming into a network device and then out of a network device. And so they come in, and it turns out that we've got queues on both sides, but this is really about what do we do with packets going out of a router. And what we're going to find out is that there's a couple of ways to handle queues, scheduling of the queues, and then if we really run into trouble, what else can we do? And then our four characteristics of quality of service included bandwidth, right? What was our capacity? And then we had delay, jitter, and packet loss. Now, delay is also known as latency, and we can measure that one way or two way. So you can measure it just from me to you, or I can see how long it takes you to respond after I send you something. Jitter was the variation in packet arrival time. And then packet loss, killer for TCP applications, right? You lose a packet in TCP, and the TCP sender has to really back off on what's happening. We'll talk a little bit more about that later on. Now, the whole idea here is that if you've got important applications, then what you're going to do is elevate or prefer one application or another, or over another. Or you might say, well, that's sort of garbage, and so I'm going to put that behind everybody else. And remember that when we're talking about classification and marking, they can be applied at layer 2 or layer 3. So last time we talked about the 802.1 queue header at layer 2 and those priority bits. There were 3 of them. That gives us 8 different values from 0 to 7. And that can be mapped to the IP type of service or precedence bits. Now, much more important today probably is the DSCP bits. But a really good question is, how do those DSCP bits in the IP header get set? And the answer is that we look at traffic, we classify traffic, and then we decide what we want to do based on a mark that we're going to put on that packet. And the mark in this case is either going to be those 802.1q bits or the DSCP bits or both, because it turns out that we can map what's going on between the layers to each other. So once we get packets marked going into a network, now we don't have to process all of those fields. You don't have to say, well, this IP address to that IP address and this kind of protocol is going to be given this kind of preference. No, you just say, oh, there's that mark. I know what I'm supposed to do with that. So the mark in this case is in the IP header. And these were a couple of examples that I showed you last time, right? So this is the 802.1q priority. And if you don't remember, whenever you have lots of VLANs, you've got trunks. And 802.1q is the trunking protocol. That's the industry standard. So we have these layer 2 priorities. And you can see that in an Ethernet header, the actual ether type changes when you're doing trunking to 8100. Normally, we would see 0800 for IPv4, 0806 for ARP, but here we're going to see 8100, which means to a receiving switch, oh, we've inserted this 802.1q header that includes the VLAN ID and that priority. Now, this value can be mapped to a value at layer 3, and so here are are DSCP or Differentiated Services Code points. And these are the bits that we set in the IP header. So there are 6 bits, so we have 64 possibilities that we can set. And there are a couple of standard settings. Those were the per hop behaviors that we use. So a router sees these, and we have sort of some standard mappings that we use at layer 3. Those were the per hop behaviors. Okay, so if you look above me here, right here we can see this is a switch port, right? G1 or G1029, and it's got this input and output queue. We can also see that there's a queuing strategy here called FIFO. That is first in, first out. So all right, so we'll refer to this periodically. So what this means for us is that here we've got a particular port that has the ability to take packets in and send packets out. And so what we're going to do now is discuss how in the world that all happens. So all devices have queues, and if the outgoing interface is busy, right? So I've got all these packets coming in, or I've got packets from other ports that have to go out this particular port. What if this output queue is busy? We have to decide what to do about that. Now, as we go along here, we'll remind ourselves that routers have other stuff to do. It's easy to make a router pretty busy. So we get access control lists, network address translation. So there's a whole bunch of things that a router has to do that might affect the output queue or be affected by what's happening in the output queue. And then we can divide these queues up depending on what we want to do with our traffic. So you might say, well, we're going to identify that we have a couple of applications, and so we're going to divvy up our queues amongst different classes of traffic. And so to figure all that stuff out, we have something called a scheduler. And the scheduler's job is to decide what message gets transmitted next. Now, if it's very straightforward, right? That one came in, it goes out. That one came in, it goes out. Then it's really no big deal, as long as we can keep up with the traffic. But when we've got special traffic or when we've got problems, now we've got to decide some additional stuff we might need to do. If this queue fills up, you can see that we've got drops here, and we've got this output queue, the size, and then we got our maximum. You can see that if the queue gets busy, right? Now 40 doesn't seem like a big number to me. So if I throw 40 frames at this thing, what does it do with that 41st frame? Well, the answer is that it might dump the message, that last one in. So the one that goes over the queue, the switch or the router might say, I'm sorry, I can't do anything with you. I'm going to just drop you. Now what the scheduler can do then is, if we've got these different ways of breaking up our queues, then the scheduler can say, well, that part of the queue is more important than this part, or I'm going to change the way that I would normally process traffic and decide who goes out next. So here is an example where we've got packets coming in, right? This is from Tom Herbert. And so these packets come in, we got different queues, right? If this was just either a FIFO thing or we were just doing fair queuing, where everybody takes one at a time, we would grab, one from this first queue, one from the second queue, one from the last queue, go back up here, grab one, like that. But you can see that that's not what happened here. In this case, we grabbed one from the top queue, we grabbed one from the bottom queue, we grabbed another one from the top queue, and then we grabbed one from the middle queue. So that means that these two queues on the bottom might have a similar priority, but this one up here might have a higher priority or precedence over the other ones. And so that's an example of how we might schedule the queues differently. So the question is, how do we schedule all of these departures? Well, FIFO you saw from the previous example, right? That was just on a regular switch. I didn't monkey around with it. That FIFO is the default queuing strategy or scheduling algorithm that we see on a lot of ports. And it just means first in, first out, which means that packets come into a device. So if you just imagine a 2-port router, packets come into the device, and then maybe packet 1, packet 2, packet 3. Well, the first one out is going to be packet 1, then packet 2, then packet 3. So that's FIFO. This is no different than you waiting in a sandwich shop or you get your groceries and you're going through the cashier. The first one into that line is the first one that is served. Now, if we have multiple queues, and we say, I'm going to take one from that queue, then this queue, then this queue, and then go back to the beginning, and then so on, that's just round robin. So round robin says, I'm just going to do same prioritization for everybody and just rotate through. Now, on the bottom of that last slide, what you saw was that one of the queues was given priority. So in that case, we have weighted round robin. So that top queue might have been given a higher priority. In fact, it might have been given a priority that said it got twice the bandwidth of any other application or any other queue. And so what the scheduler does then is says, I'm going to take one from that queue that's got the highest priority, grab one from another queue, then go back up, then grab another one from a different queue, and so on. Now, an extension of this is what we call class-based weighted fair queuing, which simply means that the user defines the classes. Now you can do this a couple ways. You can say this is really important traffic, and so we're going to say that's a gold class. So you might lump a couple of things into that class, and then we do silver classes, bronze class, and then maybe a garbage class. Or you might specify a particular application. So anything to do with the finance or marketing department that might have a really high priority, and other kinds of traffic like FTP or management traffic might have a lower priority. So in the book example, there's a couple of different applications or a couple of different classes that are defined. One of them gets 20% of the bandwidth, one gets 30, and one gets 50. Now the one that's guaranteed 50% of the bandwidth, right, is an important application, and then the other two are guaranteed 20 and 30% respectively. Now the way that this works is that in the presence of congestion, or in the presence of limited capacity, those applications are guaranteed to have that percentage of the bandwidth. Without congestion, you might actually get more because you don't know what the other applications are doing. So let's say that the important application is running all of this data and nobody's FTPing. It might actually expand to be 55 or 60% of the bandwidth. But no matter what, in times of trouble, that percentage of the bandwidth is guaranteed. Okay, so that's FIFO, and we got round robin, and then we've got weighted round robin, and then we've got class-based weighted fair queuing. Okay, what if we have a really important app that has really stringent requirements for performance? That is where we use low latency queuing, or LLQ. Now the example that we have here is voice or video, and in particular, interactive voice or video, where you're talking to somebody maybe over the phone, or you've got a Zoom call or something like that, and you need good performance. And in this case, good performance means low latency, low jitter, and low loss. That is where you use low latency queuing. And the reason that low latency queuing is there is because round robin in this case is not sufficient, right? You could easily drop packets unintentionally. And on top of that, voice and video throw a lot of packets at the network. They're not very big packets, but they throw a lot of packets all at once. So we have this special queue called low latency queuing. So now whenever there's packets in there, that's the queue that you handle. Now this presents another problem. Anytime that you have a priority applied to one kind of traffic, that means other traffic that's important but not as important might be starved. In other words, if you say, listen, this voice is really important, it's got to get through no matter what, whenever you see packets here, send them. If there's a lot of them, well then anything else would get starved out, wouldn't get sent. So there are other techniques that we can use to prevent that starvation. And so that's what policing is all about, or policies, or call admission control, where we can say, listen, we're going to service that queue, but if there are overages, we're going to kill off some traffic so that we can service the other queues. So here is our overall strategy. You can use round robin queuing, so a method like class-based weighted fair queuing, for data classes, right? Non-interactive. So these are all your web traffic, FTP, data moving back and forth, things like that. But of course, they're going to be weighted towards your business critical applications. So if you've got a system where you're taking a lot of orders or something like that, where there's a lot of support going on, then we want to make sure that that traffic is prioritized, but the other ones will still get some capacity. The low latency queuing will be for our interactive real-time transmissions like voice and video. Other kinds of telemetry are sometimes really important too. Now, we also put voice and video in separate queues. Now, we're going to talk about policing here in a second, but what we want to be able to do is apply whatever techniques we're using to each queue. If we dumped all the voice and video into one really high priority, low latency queuing queue, then it would sort of monopolize what we were doing. And we would treat all that stuff the same. But if we have voice and video both happening but in different queues, then we can apply the same techniques to the video queue that we did to the voice queue. And we'll see exactly what that means here in a second. But it means that you can treat their behavior independently. And then another part of this, it's not on the exam, but it's the call admission control, which allows us to have a few more tools in our toolbox to prevent injecting too much voice or video into the network, right? It's another control. So moving on from queuing to shaping and policing, these are specialized tools. A lot of times they're found at the edge of your network, and you can see on right above me here, we're generating all of this traffic and we're sending it out to the internet. And right here on this router is going to be some ability to affect what's going on the traffic. In both cases, we're going to monitor the bit rates of the messages flowing through the device. We're just going to take a different approach. Now, the key idea here is that you paid for bandwidth. So this pipe out here has a cost associated with it. And you don't want to just throw bandwidth at it, because the service provider has a couple of responses to that. They could say, well, listen, you've paid for a certain amount of capacity and you sent us all this data above that, so we're going to send you a huge bill because of it, because of your overages, or we're going to cut the traffic off, or somewhere in between. So we have to remember that what we're talking about is a WAN link that has a cost associated with it. The book example is that, yes, you have Metro E, and yes, it's a fiber connection, and yes, it's gigabit. But there's nothing at all that says, as a service provider, I know that our physical connection is a gigabit, but there's nothing at all that says I have to handle a gigabit of traffic from you. You paid for 200 megabits per second, and that's what I'm going to allow you to do. The policers and the shapers, they both have the goal of keeping you at that 200 megabits per second, right? So this is the whole capacity and you're supposed to be down here. What the policer does is it drops traffic. It says, whoa, we're over, so I'm going to cut off the traffic that's over. And the shaper says, wait a minute, let's never get there. Let's never get to that point. So if we feel like we're getting up to that bit rate, I'm going to slow the sending down by holding things in the queue. So the two approaches here are you out of the pool and hold on a sec. The water slide is not clear. Let's wait till that person gets down there. Now you can go. Now I'll point out the graphics first above me here. Here's our policing, right? So here is the bandwidth that you paid for, this dotted line right here. And what the policer does, or the policing does, is it cuts off all of this traffic that's over the bit rate. Now, sometimes there's another line here that says you can burst above that for a certain amount of time, and as long as you go back down, it's not going to be a problem. But straight out of the box, what it does without any additional configuration is it says, here's my limit, here's my threshold. I'm going to cut off anything that's over that bit rate. As opposed to the same problem, but with a shaper. And the shaper says, well, let's make sure that we hold things so that we just keep things constant. And so if there's a lot of traffic flowing, then the shaper holds things in the queues and releases things so that we stay right at that bit rate. Okay, so let's cover this. Policing, or the policy, says at the edge of the service provider network, traffic comes in that exceeds the customer's paid committed information rate, or CIR. You could discard the traffic or remark it for potential discard. So it's not a guarantee that your traffic is going to be killed off. But the service provider certainly could do that. But they might say, all right, look, we're not experiencing a congestion problem now. We're going to let this traffic go, but we're going to remark it. We're going to change the mark on there. So if there is a problem, that's the first traffic that goes. If you continually go over your committed information rate, they might say, look, it's time for you to buy a little more bandwidth. Now, shaping, instead of risk losing your data via discard, you might shape your traffic on its way out there so that you never go over the committed information rate. Or if you're approaching it, that's when you say, oh, all right, hold on, it's like, let's slow things down. So shapers slow down the messages through queuing them. They keep them in the queues longer, and there's a time interval. So let's see if we can unpack this a little bit. If you paid for 200 megabits per second out of 1,000 megabits per second, or a gig, that means that you can send for 20% of the time. But if you say, all right, we're gonna flood the zone for the first 20% of 1 second, and then we're not going to send for the rest of that second, right? Or if we think about 10 seconds, we're going to send lots of traffic for 2 seconds, and then we're not going to send anything for 8 seconds. Well, that would be a kind of a crazy way to go, because everybody would have to wait for 8 seconds in that case before they could be transmitted, which might kill off a whole bunch of your applications, especially those that are real time, that require interaction. So instead, we think in terms of very, very short timing sequences. So instead of thinking about 10 seconds or 100 seconds, think in terms of 1 second. So we might send for 200 milliseconds and then just slow down traffic for 800 milliseconds. But that might cause problems too, because we know that voice has one-way latency as a target. So we might then say, well, instead of the 1 second time frame, let's think in terms of the 10 millisecond time frame. And so now we're talking about saying, well, we're going to transmit for 2 milliseconds and be quiet for 8 milliseconds. And so that might be another way to get by that. And by thinking in terms of really, really short time periods, we don't cause problems for our applications that are time sensitive. So hopefully that makes sense to you. Okay, so the last part of the chapter is about congestion avoidance. Now this is really TCP's game. So remember how TCP sliding windows work, right? Both parties in a conversation say, well, listen, we're going to do that handshake at the beginning of TCP, and I'm going to tell you what my window is, and you're going to tell me what your window is. And when we're sending traffic back and forth, you have your window, I have my window, but I'm also going to keep track of your window, and you're going to keep track of my window, and how much stuff we sent. Okay, the window size is unacknowledged bytes. Remember, the sequence and acknowledgement numbers are actually byte counts. If you close down a window, meaning that if I had a 10,000 byte window and you sent me 10,000 bytes, the window's closed, in which case you have to stop sending me data until I acknowledge what you sent me. Now, if we get done with a segment, right, a chunk of data, and we go, the network's working pretty well, we can adjust the window size up. And a lot of times that's a doubling. And eventually you get to the point where the receiver and the sender, or the two senders, never have to stop sending. They just send data nonstop because now the windows are so large. And this is also where we get a window scaling factor from. But what happens when a packet is lost? Remember that packet loss is a real problem for TCP senders. Why? Because they're keeping track of all the data that they sent, and they go, you know, I got acknowledgments about everything else but that chunk of data, and I will have to resend that. In the event of a lost packet, we have to adjust our window size, and a lot of times the window size is cut in half. Now, if we think about that for a second, we go, okay, if that's TCP's behavior, right? If that's the way that TCP deals with things in terms of congestion, it's also how it keeps track of all the data that's been sent. What if a router was having trouble with congestion? What it could do is occasionally drop a packet from a TCP sender. So if you got this router that's just getting hammered with traffic, right? Wow, all this traffic's coming. The router could look at its queue and it could say, I'm going to kill that packet right there. And that TCP sender would automatically slow down what it's doing because it's got to figure out what to do about that packet. Now that might clear up the queue problem. It might clear up the congestion problem. So by default, routers do something called tail drop, which means if the queue is full, right, and my queue is filling up, and then another packet comes in, that 41st, right, then the router just says, I don't have any more room, you're done. Now that right there might stop that TCP sender or slow it down. But we can actually do something called weighted tail drop, which says, well, look, my queues are okay now, I'm not going to do anything. But if my queues get a little fuller, I'm going to do some either random tail drops, or I'm going to do weighted tail drop, which says I've got these classes out there. I know some are important. I know some are not so important. I'm going to drop one from maybe one that's not so important, or just randomly. If the queue gets full, then we're going to start dropping things. Okay, so here is an example right above me again. I've got packets coming in. I've got packets going out. And, you know, if we stay below this minimum threshold, I'm not going to drop anybody. Life is good. But if I get in between my minimum and my maximum threshold, I'm going to do some random dropping, right? And that'll keep me from having a congestion problem. And then, of course, we go over the threshold and we just drop things from our TCP senders especially. So the last note here is that some senders can be classified as less or more likely to be dropped, right? If you've got FTP, which is not interactive, it's just somebody waiting for stuff, that might be a good application to say, look, you are filling up my queues, I need to slow you down. All right, let's do our do you know this already questions. Remember that we did questions 1, 2, and 3 in the last video. Question number 4, which of the following behaviors are applied to a low latency queue in a Cisco router or switch? Remember that these are the ones that have low packet loss, low latency, low jitter requirements. We could do policing, right? We could keep those queues at a particular level, and we could also do priority scheduling for those queues. The minute you have something that's in LLQ, we're going to have priority scheduling for that queue. Question number 5, think about a policing function that is currently working, and also think about a shaping function that is also currently working. That is, the current bit rate of traffic exceeds the respective policing and shaping rates. So we went over. What do we do now? Which statements are true of these features? Okay, so what would a policer do? Well, remember that the service provider might say, I'm going to cut you off. Or it might say, I'm going to remark that and not do anything. So a policer may or may not act. The shaper is on the other side of that connection, and so it definitely queues. When you're over, that shaper is automatically going to say, all right, let's slow things down. Let's keep things in the queues a little bit. So that was A and D. Question number 6. A queuing system has 3 queues serviced with round-robin scheduling. So they're just going pop, 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 pop. But then it's got one low-latency queue that holds all the voice traffic. The round-robin queue 1 holds predominantly UDP traffic, while round-robin queues 2 and 3 hold predominantly TCP traffic. The packets in each queue happen to have a variety of DSCP markings per the QoS design. In which queues would it make sense to use congestion avoidance or some kind of drop management tool? Okay, so this is where our knowledge of TCP comes in. If you drop a packet from UDP, that UDP sender doesn't slow down at all. It doesn't care. But if you drop a packet from a TCP sender, then it's got to respond to that. And so both queues 2 and 3 have TCP traffic in them, so those were our answers, C and D. So our Chapter 12 look ahead, it has the very clear title of Miscellaneous IP Services. But if you look at the topics, it's going to be really a lot about a router redundancy, right? We got a couple of pathways off of our network, but we're only using one because we've got some failover. So there's a couple of things that we're going to look at. First hop redundancy protocol, IP routing or router redundancy protocol, hot standby routing, virtual router redundancy protocol. So there's actually a collection of these that look at failover or redundancy for your external connection. And then there's some other IP services that we use, simple network management and file transfer, trivial file transfer protocols. So a couple of extra services we're going to look at. All right, this has been Quality of Service Part 2. We did queuing and policing and shaping, also a little bit on congestion control. And all of these techniques really are based on the classification and marking that you will have already done. So that's the first thing you have to do, right? Classify, then you mark, and then you say, okay, based on the marks that we see, this is what we're going to do with our strategies. And we know now that that stuff exists at layer 2 and layer 3. Now, in the demo videos that I've done, the builds that I've done that I'll also link here, what we do is we set up a policy that says, here's our marking and here's what we want to do about that. And here's where we want to do something. In the case of policies, what we first do is set up a class map that does our classification for us. We do a policy map that specifies the treatment, those bandwidth percentages, and then we do a service policy, which applies our treatment on an interface and a direction. So those three sets of commands go together very handily. All right, like and subscribe for router redundancy and more service protocols. May those packets always reach their destination, whether you're policed or shaped. And hey, this is CCNA. We're networking. We're really moving up here. We got some stuff in our toolbox. You can do this.